From a tailor measuring cloth to a doctor checking a temperature, daily life relies on specific numbers. But these numbers only work if we agree on what they mean. If a shopkeeper and a customer use different starting points for a unit, the simple act of weighing grain becomes a dispute. On a larger scale, these inconsistencies create friction. International trade slows down when manufacturing specs don't match, and scientific research becomes difficult to verify when data from one lab cannot be easily compared to another. To interact with the world reliably, we need a shared language to quantify what we see. This need for a common reference point is the foundation of measurement in science. Formally, measurement is the process of comparing an unknown physical quantity against a known standardized quantity of the same kind. Essentially, we are asking, how many times does this standard unit fit into this object? We express this relationship mathematically. A physical quantity is equal to a numerical value multiplied by a unit, or Q equals N times U. A numerical value on its own doesn't describe the physical world. If you just have the number 5, you have no information. Is it 5 meters, 5 kilograms, 5 seconds? The unit is what provides the necessary context. In physics, a number without a unit is an incomplete measurement. For a magnitude to have scientific meaning, it must be paired with a specific, defined unit. Different regions once relied on their own isolated systems. One lab might use CGS, centimeters, grams, and seconds, while another used the FPS system of feet, pounds, and seconds. These differences forced researchers to spend more time converting data than analyzing it. This led to the MKS system, which focused on the meter, kilogram, and second. This served as a bridge toward a more comprehensive global standard. Today, we use the SI system, or the International System of Units. It defines 7 fundamental base quantities: length in meters, mass in kilograms, time in seconds, temperature in Kelvin, electric current in amperes, luminous intensity in candelas, and amount of substance in moles. By adopting SI, the global scientific community has a common framework. It allows researchers to synchronize their results and reduces the risk of errors that occur when translating data between different regional standards. To see how units affect the math, imagine measuring a classroom floor with 3 different sticks. If the sticks have lengths in a ratio of 1 to 2 to 3, the group with the smallest stick counts 30 units, while the group with the longest counts only 10. There is an inverse relationship here. When the size of the unit increases, the numerical value needed to describe the same space decreases. Mathematically, we say Q equals N1U1, which also equals N2U2. The physical quantity of the floor, Q, hasn't changed. Only the numbers and units have adjusted to one another. While the numbers we use shift based on the size of the unit we choose, the physical quantity we are measuring stays constant. Because the physical quantity remains the same even when we change the unit, we can use the relationship N1U1 equals N2U2 to convert between systems. For example, to convert 9 kilometers per hour into meters per second, we substitute the known equivalents: 1,000 meters for every kilometer and 3,600 seconds for every hour. 9 times 1,000 divided by 3,600 gives us a value of 2.5 meters per second. A standard shortcut for speed is to multiply your kilometers per hour value by 5/18 to find meters per second. To go the other way, multiply the meters per second by 18/5. We can apply this to force as well. 1 Newton is 1 kilogram meter per second squared. By substituting 1,000 grams for the kilogram and 100 centimeters for the meter, we find that 1 Newton is equivalent to 100,000, or 10 to the power of 5 dyne. These conversion rules allow us to share data across different scales, ensuring that a force calculated in a laboratory remains consistent when applied to heavy engineering. It's important to note a common point of confusion regarding mass. Because the word kilogram has a prefix, many assume the gram is the SI base unit. In the SI system, however, the kilogram is the official base unit. Also, remember that different numerical results don't necessarily indicate different physical quantities. As long as the units are different, 2 different numbers can describe the exact same length or mass. We observe a quantity, quantify it using magnitude and units, and then use the SI system to ensure that our measurements are recognized globally. But measuring something at rest is just the beginning. Our understanding of measurement will be tested even further once the objects we observe start moving. Science can only describe the universe when we have a shared language to measure it. Agreeing on that language is the first step toward understanding how the world works.